Start, sir.
Yes,
Shall we begin the sir?
yes. Good morning. Am I
Yes,
audible?
sir. Yes, sir. Yes, sir. So our students will host the session, sir.
Okay, fine. Okay, fine.
Okay.
Good morning to one and all. I am Gayatri, and on behalf of the Department of Computer Applications, I warmly welcome you all to the fifth and final day of our 5-day faculty development program on quantum computing and its applications. It has been a rewarding journey over the past 4 days, filled with thought-provoking sessions and rich enlightening sharing. We are truly grateful for the active participation and interest shown by each one of you. Before we proceed, a quick announcement for the participants. Please keep your microphone muted to avoid the background disturbances. If you have any questions during the session, kindly type them in the chat window. Selected questions will be addressed at the end. Please keep your video turned off. Feedback link will be shared in the chat towards the end of the session. Now, I invite Sweta to welcome our resource person.
It's my pleasure to introduce today's resource person, Mr. Saji Mohan PC, scientist at CDAC Thiruvananthapuram. He holds a BTech in Computer Science and MTech in Cybersecurity from Amrita University. With 19 years of experience at CDAC, he has contributed to key projects like STR for naval communications, MANET, and quantum key distribution networks. His research spans embedded system, software-defined networking, and quantum communication security. He has authored several research papers in reputed journals and holds a patent in SDN routing algorithms. Today, he will speak on the topic quantum key distribution, a vital component of secure quantum communication systems. We are honored to have him with us today. Now, I hand over the session to Mr. Saji Mohan, PC. Once again, I welcome you, sir.
Thank you. I'm starting my presentation. Yes, I am Sajmohan PC, working in CDAC Tirunduram under the cybersecurity section. I have presently in the quantum key distribution network, focusing on the software-defined quantum key distribution network. Today, we are going with this agenda. First one, just look on the quantum computing and threats. You might have already on the previous day sessions, you covered the what is quantum computer, what is a qubit, and what are the processing capabilities, the threats, all things you might have heard about that. And going after that, I am little bit moving about the post-quantum cryptography and the quantum key distribution. Both are the solutions for the quantum threats, quantum computing threats. After that, just going with the software-defined networking. What is the software-defined networking? Only a little bit information about you. You might have heard about the SDN concepts. And next one is we are going with the key part, software-defined quantum key distribution network. And then going with the architecture and the integrated simulator, which we have developed, and one use case going to cover with the Macan network. Presently, I am in the participating and developing in the Macan and the interoperable STQ area. Yeah, introduction to the quantum computing. In the previous day, you might have heard about the qubits. Like in the classical computer, bits are there, 0 or 1 states are there. Qubits is can exist in the superposition of both 0 and 1 simultaneously. Many states are possible based on the spinor direction. Another advantage is the superposition of qubits to exist in the multiple states. That's one. It enables the quantum computer to perform many calculations simultaneously. That means the enormous computing power has come. For the classical computer, it takes too much time using this quantum computing. The computation power is very high due to the quantum properties or the quantum computer. that will solve complex problems in a small time. Another one is the quantum entanglement, the state of one qubit directly linked to other, regardless of the distance. The state of the one qubit is directly linked to another. It is the entangled pattern that can communicate with a longer distance and faster processing of algorithms. Let us consider the one scenario based on the quantum physics. You can see both parties are communicating. One left side, you can see Alice is there. On the right side, you can see Bob. Alice wishes to communicate to the Bob. In the quantum channel, using the quantum computing, the qubits at the Alice side is generated and transferred it to the quantum channel. It may be on the fiber channel or free space QKD or satellite link maybe. Then the other side, Bob, the photon detectors are there, they detect, and based on the quantum transmission, it generates the key. And the authentication of communication is happening through the classic channel. I am going to cover with the many limitations at that. Only key generation is the part of the quantum channel. Using the quantum communication, the key generation is happening only through this one. All other data and other communication is going to the classical channel only. In this state, due to the inherent property of quantum computing, one person, like in the picture is Kevin in the upper side, is trying to measure. Then an error is detected by the Bob. When a third party or Eve or Kevin is trying to measure the qubits transferring to the quantum channel, on the other party, on the receiver party is detected error is happening and someone is dropping. Then the QR rate will go high and the communication will collapse. Based on the quantum properties, it will detect any unauthorized access in the channel. This is the basic principle of the communication. Let us go with the quantum computers. Like many vendors are there. The IBM is one of the major giant in the quantum computing. They have introduced many type of quantum computers. They are also providing the cloud access of your computer. Suppose you have an algorithm to execute in the quantum computer. They will provide the online service. You just enter through a login and you can execute it using their toolkit. Another one is Google's involvement. The latest one is Willow processor that is capable of the high computation power, or they can solve the complex algorithm in a small time. In 2019, they have already announced the quantum supremacy. I am going to the next slide. And the Microsoft involvement is there, and the D-Waves are done. Many giants are there. They are the commercial quantum computers are available now. They are capable of breaking some classical algorithms. Coming to the quantum supremacy, it means that the quantum supremacy means that they can solve a task in a defined time frame. Suppose 1 second or 200 seconds or 1 hour, 2 hour. Using the supercomputers or classical computers requires 10,000 years. Using using a quantum computer, they can break the classical algorithm in the defined time. And they announced in 2019 they have acquired the quantum supremacy. They could able to break the keys in 2000 seconds. That may be the another one. Similarly, the IBM Eagles was also capable of doing that work. And the development of quantum computers is going in the high momentum, high speed. And within the 2030 or 2035, many commercial quantum computers is able to available with the high computation power. Previously, I introduced some quantum computing aspects and computation power and quantum supremacy. Why it goes to a threat? because the quantum computers can solve complex algorithms in a very short time. That is the problem. They have explained the Short's algorithm is there, Peterson algorithm is there. Those algorithms can break RSA, ECC, or which is we are using presently in our communication. Suppose we are sending an email presently now, or the sending the file transfer and the saving data in banks and communication. Any communication using the public key infrastructure, it should be under a threat. Suppose one party is, suppose I need to communicate with your college. Then I have the public key of yourself, your college, and you have your own private key. When I send a message to your college, I am using your public key to encrypt it and send it through your college. Your college is using your private key to decrypt. You consider that you can use the RSA ECC algorithm presently using. The algorithm itself says you cannot derive the private key from the public key using the classical computers. It may take many years to break. The RSA algorithm states that it is due to the time complexity, the time complexity, time required to derive the public key from derive the private key from public key, that may take more time. That is that way they ensure the security. The algorithms related to this side under threat because quantum computers has many capabilities, parallel computation process, many representation. They can derive a private key from public key. Suppose I am encrypting a message from myself to your college using the public key of yourself. On the way, on the channel itself, another party with quantum computer can intercept this message and derive the private key from the public key of yourself, and they can decode it. They will be able to access the entire content. That is why the security of the banking, e-commerce, and national security infrastructures will be under a threat. Another one is the key exchange protocols. Diffie, Helvan, and similar methods that risk from the quantum attacks. I already mentioned that the quantum computers efficiently solve discrete logarithm underneath the key security. The key exchange threatens the confidentiality of the communication. When the quantum computers achieves their supremacy or publicly available the quantum computers in the market, it will definitely a threat to our present communications. All present communication using the public key infrastructure. Another one is that it is not in the thread of the future communication, it is also a threat in the previous data stored in drives of database vulnerable to future decryption. Suppose one data encrypted using the public key infrastructure stored in the database of banks or financial institutions or military, then it may be under trouble. Also in the data in transit, real-time communication also at risk. That requires immediate and ongoing proactive measures. I summarize the encryption in the post-quantum era. That means after achieving the supremacy, after the introduction of quantum computers, which is capable to break the PK, RSA algorithm, public key algorithms, then the plain text encrypted on the Ali side is transferred to the both side. For the under below, you can see an Eve. Eve is trying to decrypt using the classical computer. That means the current computer or supercomputer. It may not be possible. It will not possible. But using in the above side, Kevin is there. Kevin is having the quantum computer. The using quantum computer, they are trying to derive the private key from the public key. It is possible when quantum computers are in action, and the entire communication will collapse. That will be under threat. The current system will be under very much threat. Then I mentioned about the some algorithms. That means that the PKI is under threat. But what about the symmetric encryption? Suppose you are using the same key at both ends. Symmetric encryption are safe even in the post-computing area. Post-quantum era. It is safe because the key size should be in high. The key size needs to be a large size in order to avoid the breaking of the symmetric encryption. The quantum computers also trying to transfer a key from one to another end using the quantum channel, and communication is happening through the same symmetric key. That is the way to deal with. Already mentioned about the communication of mail. Suppose I am sending a Gmail or accessing the web server and other things. The TLS and SSL is there. That will be under a threat. It can be broken after the quantum computer is in action. And the current internet security is under threat. That is sure. They predict that after 2030 or 2035, it will definitely cause a large scale problem. It may affect on the common people also. Some of the threats, most of them are already discussed. One is the quantum computers threaten traditional encryption PKI methods based on the mathematical complexity. Algorithms with mathematical complexity will cause a threat. Another is the encrypted data. Some data are in the bank or financial institutions. Quantum computers can decrypt it. It may be a threat for the existing data. In the national security banking, that data should be a high risk because those data needs a long-term secrecy. The applications like Bitcoin and cryptocurrencies will be under a threat. Also, attackers can reverse engineer the private keys and access the wallets. Using the quantum computers, it is able to get the access of your wallets, cryptocurrency wallets, and cryptocurrency exchanges that may be under threat. Another one is the thread is the thread itself rising from the QKD quantum key system itself. Then there may be a practical implementation flaws may be there in there may some theoretically it may be correct, but the practical implementation lacks some security threats, and some weakness may be in the quantum computers itself and the QKD implementation, like manipulating bits and introducing noise. One can make, suppose you are communicating from one Alice to another Bob machine, one party can introduce the noise, can damage the channel, or they can trying to manipulate the qubits. That may be also a one problem you need to consider it. These are the threats, common and major threats for the quantum computing and threats for its applications. Then another one is the main question: how to protect internet security. After quantum supremacy, quantum computers can break the public PK public key infrastructure. What is the solution? In 2016 onwards, the companies, major standardization agencies are starting their work related to protect the internet security. One thing is the post-quantum cryptography, that is named as PQC, post-quantum cryptography. Another one is the QKD, quantum key distribution. Those two solutions are there to prevent this quantum attack. The first one is post-quantum cryptography. It mainly deals with the software algorithms only. There is no infrastructure is required. The algorithms is changing. Suppose you can see the TLS, SSL certificates are there, TLS cyber suits are there, RSA algorithms are there. Instead of this algorithm, some algorithm that is quantum safe. Quantum computer cannot break. Algorithms can introduce and use the key encapsulation mechanism and use the key to exchange from one party to another party, and you can use the algorithm. There are many challenges involved in the PQC part also. And the second one is the quantum key distribution. Mainly, it focuses on the development of new infrastructure. The QKD nodes are required highly complicated one, costly one, need the complex electronic schematics are required for development. Also, that requires optics channel, dedicated optics channels are required. Presently, the fiber channels are required. Another ways you can use the satellite-based QKD, free space QKDs. Many other methods are there. It definitely requires a huge investment. And presently, this quantum key distribution communication is focused. Quantum key distribution is focusing on ensuring the security of military purposes and financial things. And further, it will definitely move it to the common person requirements. Let's first look on the post-quantum cryptography. Post-quantum cryptography means that the algorithms designed to be secure against attacks from the quantum computers. Suppose you mentioned that the RSA algorithm is there. RSA algorithm is generating two keys. One is public and private key, but the private key can be derived using the public key. That may take more time at that time. The time complexity of decryption of these algorithms is generating the private key is time consuming one. That needs to be avoided. Then using the post-quantum cryptography algorithms, we can use the same PKI infrastructure, but we need to update the algorithms. Some algorithms are capable of quantum computer threats. Using the certain algorithms, quantum computers cannot derive the key, the one key using the other key pair. Both key pairs are there. Using the one key, we cannot derive the other key using the quantum safe algorithms that comes under the post-quantum cryptography. Then coming to the open source part, there are many open source projects are there. Mainly OKS project is there for the collaborative development. It is standardization agency is there. NIST is the coordinating. They started work in 2006. They are inviting the submission for the quantum safe algorithms. Many companies are participated, and presently the standardization is going on, and it is also compatibility with the classical system. Only you need to change the algorithms, and it is efficient and scalable, but the many threats are there. Another thing is the hybrid approach. Most of the Amazon cloud and some other solutions presently using the hybrid approach. They are using the PKI and the PQC for their security, for their securing their cloud and other things. You can see the hybrid key approaches. They are clubbing with the PKI key plus the keys generated using the PQC, and they are ensuring the security. This one is the hybrid approach. They plan to transition. The transition means gradually transit it to the PQC part. For the current communication, they are partially introducing the PQC key, and the first part itself is a PKI key, and the second part they are using is the PQC key, gradually transferring from PKI key to PQC key. In future, they will definitely go with the PQC only. Coming to the standardization of PQC part, the project launched in 2016, and they have received four round submissions and reviewing. On the reviewing part, many companies can break their algorithm using the part. After the clearing of the algorithms, when the algorithm is considered as a quantum safe, it goes to the another round. Presently they are in the round for submission, and they are evaluating. They will evaluate it on the September 2024 for the next round evaluation. This one is the one project is open quantum safe project is there. They are mainly it is a focus open source. They are mainly focusing on the algorithms which are part of the NIST submissions. The PQC algorithms, when a submission is going on in the NIST, round 3, round 4, they will introduce an algorithm. The algorithm will be available open source. You can also use. They will provide the library. That library will support Go, C++, Java, and other programming languages. Using this open content safe project, you can integrate the open SSL using the PQC algorithms. The library includes the C featuring programs, and OpenSSL is provided integrated the PQC algorithm is there, and using the browser we can also integrate the PQC in the web application for practical use, and many language support is there. The limitations of these PQCs are not standardized yet. Standardization procedure started in 2016, but after the 9 years, it is not completed. Submissions are going on, and the standardization procedures are going on because quantum computers are not introduced yet into the full functional. That is why they couldn't guarantee. They didn't prove the algorithm in the present algorithms submitted in the NIST submission part as the PQC for the PQC are not proven against quantum computers. In future, after 2 or 3 years, a new capability quantum computers and new algorithms will be there, definitely there. Then someone can break the algorithm. That is a problem. That is not proven. And next one is the not guaranteed, because the standardization, 6th PQC standardization conference on algorithms qualified on round 3. They have every round 3 submission. They have several rounds and submissions are there, and the standardization conferences are there, and someone is trying to break the keys. One algorithm in the round 3 is qualified for the round 4 is there, but it has been broken by some other party. They passed the round 1 submission. They passed round 2, round 3 passed. After the round 3, they have broken. That is a problem. He couldn't ensure that. You can refer this one, Open Quantum Safe project. It has many other resources. You can do some project works or some other algorithms. You can try the generate the key pair, key encapsulation. You can transfer the key. You can use the many algorithms like Kyber, Dilithium, and some other Saber algorithms. All algorithms are there. Quantum safe algorithms are. You can install it on your PC. Most of them will support under the open source platform, that may be in the Linux platform. The libraries you can use. Using this library, you can generate the PQC algorithm. You can use from those libraries, OQS libraries, in your project, in your communication. You can also use. In the first part, we covered the PQC part. PQC, two methods are there. One is the PQC, another one is the QKD, quantum key distribution. We covered only the PQC part. The PQC part, there is no requirement of infrastructure. Once again, I wind up. There is no infrastructure required. You can integrate with the current classical systems, and only you need to get the correct and quantum safe algorithms that should be passed on the NIST submissions. And another one is the quantum key distribution. This quantum key distribution is based on the quantum mechanics and the quantum properties to secure the key exchange. There are many inherent properties of the quantum mechanics are there. The one photon is transferring from one side to another one. It could not be copied. When a person tries to copy, it changes states, and the receiving party will be notified. And the eavesdropping detections are there, and also some limitations are there. The major limitations require specialized infrastructure and has range of constraints. We'll come to the detail one by one. Coming to some QKD products, IDQ is the major one in the market. They have their own QKD nodes and communication mechanisms are there. The QKD devices are same like the network devices. Only the fiber communication is happening to there. Inside the device, there are many complex circuits are there. Photon detectors is there, and transferring mechanisms are there, encoding and many other post-processing algorithms. Many complex processing are there inside this box. Toshibas initiatives are there. Many other armies QKD is from the QKD land. In zero is also some QKD nodes. ESRO is also tested them space QKD nodes. There are many devices are in the market for the QKD. Presently, it is available in the QKD. It is highly complicated, highly overpriced. Or not overpriced, it is a huge investment is required for procuring these devices. Then coming to the quantum key distribution scheme. We are going in deep the quantum key distribution scheme and then to the SDN part. In the quantum key distribution scheme, you can see one transmitter is there and one receiver is there. You can consider this QKD transmitter as an Alice, as the common time referred in the QKD distribution. On the right side, you can see the QKD receiver as a bow. The first part is the photon generation of photon and qubit encoding is there, and then transferring the qubit sequence through the quantum channel. On the receiver side, it is decoding using the photon detectors. Using this quantum channel, only qubit sequence is transferred from one side to another side. Some errors may be occur, some maybe some encoding of some basis, maybe there are some photons cannot be changed. Some photons can be changed during the transmission. Someone may be intruded or eavesdrops some photons, then the state may be changed. That will be there. Then you cannot expect the quantum bits qubit transferring from one to another is exactly same as transferred one due to the property, suppose one communication channel requires too much length or the quality of the quantum channel is very low, then there is a possibility for introducing more errors on the qubits. Then we cannot guarantee that the transferred qubit as a key. We are not able to use the transferred qubit sequence as a key. To derive the key, there are many things we need to consider. After the transferring the qubit, the error bits we need to identify, estimate, we need to estimate error occurred or not, and then we need to error correct. And then there are some procedures like the key distillation, privacy amplification is also there. That those things will happen through the classical channel only. Classical channel means person communication channel only. Ethernet communication only. After this one, key distillation, you will get the secret key of the node 1. Also, you will get the secret key of node that means the Bob. You both side. In the Ali side, you will get the secret key. And the Bob side, you will get a secret key. This secret key is symmetric key. This key will be used for the further communication in the quantum key distribution. Once again, I am repeating the part. In the QKD transmitter is there and the receiver is there. And the qubits are generating and the encoding with the basis and transferring to the quantum channel only. On the receiver side, it receives and decoding, and the shifted key will be generated here. And using the classical post-processing algorithms like error estimation, error correction, privacy amplification, those things are mentioned as distillation. You will get the key at the Ali side, also at the both side. This key is used for communication. You can implement VPN service or any other. You can use the email communication, or you can use the secret key for the secure communication. Only qubit transfer is happening through this one. The classical channel is mandatory for post-processing. So in the key distillation part, you can see some services are passing through the classical channel. Those things are called as post-processing. After the post-processing, you will get the secret key. In some more details, I'm explaining one VPN network is in below side, the classical VPN, present VPN network is I need to get the key. Suppose I use the PKI, it can break through the quantum computers. I need to get a quantum safe key that quantum computers cannot break. A new key is required. Then I implemented two systems. QKD systems are there, one at the Alice side and another at the Bob side. The fiber channel is presently quantum channel is connected here, and the raw key quantum transmission is happening through this channel, quantum channel itself. After that, the authentication, the word key shifting, error correction, privacy amplification, recognition, many steps are there. After that, I am getting the key. The classical channel is these things: authentication, key shifting, error correction, privacy amplification, key reconciliation, all are happening with the help of classical channel. After that, if the key is generated there, and the key is used for the VPN communication. It is one scenario for that. This classical part, we don't have any infrastructure, only the QKD system part and raw key exchange content channel, we need to invest more. Another is the limitation of traditional QKD. I explained about the QKD is there. There is a need to QKD devices, dedicated devices are there, complex devices are there to create and transmit the photons. Also need to detect and generate the qubits, generate the keys. Then it is good for the quantum safe communication, but it has some limitations are there. One is the point to point. Because I mentioned about the whole things communication between Alice and Bob. It is only for the point to point. One device to another device, it is possible. Using this point to point transmission, quantum transmission, we are not able to derive or create a large network. Suppose in our communication, we are not able to tell I need to communicate to you only. Suppose another channel is from communication from Trivandrum to Bangalore. One dedicated channel is required. And then I need to communicate from Trivandrum to Delhi. There is another channel is required. Another one is I need to communicate with Chennai. Then another dedicated channel is required. Using the QKD, the point-to-point network is required, but it is not feasible for them. Suppose for a large network, we are not able to maintain the one-to-one connection or point-to-point connection. That is a limitation. Using the optical switching is there, but it is only for the limited one. We are not able to create or maintain or scale to a large network using the QKD point to communication. That is the one limitations. Another one is the high cost. Already mentioned that it is a complex one. It is taking photon detectors. It is priced costly and need the specific hardware environment requirements like temperature and other things. And maintenance is a highly one. And another one is the static setup. Network is not flexible because we are not able to move the node from one side to another one because it is a fixed point to point. One heavy resource or infrastructure is there. We need to be there to get the key. It is not able to send the key over other side also, and it does not fit into the existing network well. This one is the QKD is the point to point one. Suppose I wish to make a communication scheme to purchase the two QKD nodes and connected through the fiber channel using for the quantum transmission, and it is not flexible. I am not able to plug it into the current existing network I am not able to get the keys to this part. It is the major limitation of the traditional QKD system. But QKD is safe. QKD is the only hardware solution for quantum computing attacks, but it has some certain limitations. We need to address the limitations of traditional QKDs. Distance limitation is one challenge. Once the distance of the two QKD devices is very high, the QBR will be high. We are not able to communicate with the longer distance. Presently, researchers are going on. The most of them are the 500 kilometers maximum is there. After that, they could not able to communicate using the quantum channel. Distance is the limitation. Suppose we need to plan to derive a network from Bangalore to Delhi. Direct network is not possible because there are many limitations are there. One is the distance limitation. The QKD property present developments will not allow to communicate from Bangalore to Delhi on a single channel. That is a one limitation. The researches are going on. Further researchers will come with the free space QKD and the QKD transfer using the space. Also, satellite-based QKD solutions are there. Some of the institutes are focusing on that. Those will overcome the distance limitation in future. Another, the complex and expensive hardware requirement, already mentioned, and the noise interference of quantum channels, quantum qubit error. Some properties of, suppose we are using the fiber channel for the quantum transmission, light transmission, then the quality of the channel will affect on the transmission. Then the error rate will be high, and the key generation of key rate will be limited. Suppose you for the 1, 2, 3, or 5 kilometers, also the key rate is in the 10 kbps or other things. We couldn't expect high key rate. It is only a small key rate is there. Suppose 100 kilometers, it can generate 10 kbps speed. If it is a 500 kilometers, it will reduce in the bits. That is a problem. Error rate will go high. We need to address the error estimation, error correction, and after the correction and its estimation, after the correction estimation, we need to go generate the keys. Another is the key rate limitation. Another already mentioned. Another one is the QKD protocols. There are many protocols are there. BB84 is the one, and another one is the E91 is also there. We are using the DPS, curve protocols are there. For each protocol, there are certain limitations is there, certain advantages are there, some implementations are there. But we couldn't say which one is best for the particular combination. It depends on the our requirement. Another one is the limitation is it is not a limitation of challenge, but the require a secure classical channel for post processing. Suppose post processing using the public infrastructure, it is also breakable. So we need a secure classical channel for the post processing for the derive the key after the key distillation process. I mentioned there are many challenges, limitations are there for the QKD implementation part, and how to overcome those challenges. That is another topic. One is the optical switched network for the smaller and one-to-one, it is able to communicate with the 2, 3 nodes or 5 nodes. It can be possible for maintaining the direct communications and switching the communications. It will not be a feasible solution for the large network. Another one is the routing of key using the trusted nodes. That one is the another option. Mainly we are focusing on that. The first one is the topology of a switch QKD network. The optical switch is there. You can see the A is there are 4 nodes are there, A, B, C, and D. And A is connected to the optical switch. B is also, C is also D. So you can communicate from A to D, A to C. You can also communicate from B to C, B to D, or B to A. It is possible using the optical switching for the content network, content key distribution network. Another one is the QKD network with the trusted repeaters. In this part, there are A, B, C, D, E, F. 6 nodes are there. A, B, C, D, E, and F nodes are there. Suppose we need to transfer the key from A to B, Alice to Bob. There is no issue. It is directly connected. Suppose we need to communicate with the A to C. There is no dedicated QKD channel between A to C. It is going to the B only. Under the assumption that B is under the security or secure node or the trusted node, we can able to transfer the key from A to C using the B as a trusted node. Similarly, we can I need to communicate from A to F in the QKD network. It is also possible. We can go for A to B, B to C, then C to E, and E to F. Then what will happen when C to E network is down? Then it will automatically switch to the A to B and B to D and D to E and C to F. This will happening using the SDN network. Someone mute the using the QKD network with the trusted repeaters, it is able to reroute based on the link failure or high Kubernetes rates and other things. It is possible using the network with the QKD routing. Okay. In this part, we mentioned that the QKD is there, QKD networks are there. The QKD is a 0.1. There are certain limitations are there. In order to form a large-scale network operating with the present system, present classical networking, we need some more nodes, some more technologies and the optical switch network. It is not feasible for the large scale. Rerouting it is not possible. For solving all those limitations, we are in the way to use the routing of keys using the trusted nodes. The topology is mentioned in the B, QKD network with the trusted repeaters. That is the one solution for that. Coming to the part, the routing and path switching, all other things will not be possible under the classical network. You were familiar about the classical network schemes, network switches and topologies and all. Because before that, going to the QKD network with the routing, switching, and path rerouting, all other things, we need to familiar with the concept of the classical networking and the software-defined networking. Initially, we can go for the software-defined networking, and then we can introduce the software-defined network to the QKD network. Oh, I think all of are familiar with the traditional networking system and the software-defined networking. The traditional networking system, you can see that the all things with the control plane and data plane. That means that there is a switch with the traditional network is there. The routing is also there. Controlling is also there. For the switch, we need to control and transfer the data, route the data in a single unit. There is no control beyond that. But in the introduction of the software-defined networking part, SDN, the control and data planes are separated from the network switch. The data planes is residing inside the switch, and control plane is you can place outside. It is decoupled. That introduces the feature that you can control the device from the outside. You can using the centralized controller. Using the centralized controller, you can control many devices at a time. Another one is it is a programmable one. You can add the new rules and properties push into the switches, and also possible the automation of the network operations. In the previous system, the traditional system of the networking part, you need to configure each device manually. The configuration is residing inside the switch. Configuration also, the routing and switching is also happening inside. You need to load all things. You need to configure it manually using that switch only. Presently, it is not required. Using the centralized cloud solutions or centralized controller, you can configure the switch, reroute the switch, or you can add new rules. You can automate the switch in from anywhere or using the controller. The controller is capable of configuration and programmable for many devices. That is also possible. In the SD QKD part, that one is the QKD is point to point. In the SD QKD part, we are combining the QKD and SDN for the large scale network. That is called a SDQKDN, software defined QKD, counting distribution network, for forming the large scale network with many capabilities and interoperable with the classical systems, and interoperable with the QKD solution itself. The concept SDN is introduced into the QKD. That ensures the quantum security, integrates the unbreakable security. Also, the SDN system can do consider the system like that. In this topology, on the B side, the right part, here many nodes are there. Using the SDN controller, the all nodes are connected to the SDN controller. Suppose I need to communicate from A to F. Then I inform the controller I wish to communicate with the A to F. Controller will know about the paths of A to B, B to C, A to D, B to D, and D to E, C to E, and E to F. Controller will allot the path. Controller will route the path. First go with the A to B, B to C, C to E, and E to F. After sometimes the path between the quantum QKD path between the C to F failed, or some error is raised more than the threshold value. Then controller will know that controller can able to reroute. Controller will issue commands to the B, D, E to route the particular communication from A to F, go to A to B, B to D, D to E, and E to F. It is also possible. Suppose I think this I need to communicate from the node E to F. There is no quantum link is there. Quantum link is failed. The controller can communicate using the E to F using the PQC. Classical channel is available, then controller is able to communicate using the PQC also. Suppose one direct communication is possible using the SDN controller. The multi-node A to F, there is many paths are there that is switching from through the trusted nodes that is mentioned as the key relay procedure that will be supported by the controller. And another one is if the quantum link is not available, then it is able to communicate with other node using the classical channel using the PQC algorithm. Those things are the features of the STQKDN. and it is a cost-effective solution. You can also use the PQC in the networking part also. You can integrate with the existing one also. It is also possible. Next is the SDQ architecture and all other things. Yeah, before going more on the SD QKDN part and combining QKD with the SD QKDN part, we need to know some architectures and some use cases and the integrated simulator, all other things we need to address it that. The present SDQKDN architecture introduce some layers and control plane applications, network organization, many other things are there. Similarly, the further moves to the future development of the quantum internet part. Before going to the SDQKD architecture, let us take a 5 minutes quick break. After 5 minutes, we can resume the session. Yes? Is it okay? Or shall I continue?